So, with that amusing note, let me turn this over to Jeremy. A most interesting topic, a most important topic. And Jeremy, thank you so very much.
My pleasure. So no pregnant pauses? Is that, uh, okay, here we go. So welcome to Design of Experiments for R&D. And I will just point out the focus of this course is on applying DOE principles in the R&D setting with attention to the underlying assumptions. There's quite a bit of software out there, and it's a very well-developed field over many decades. So there's all kinds of ways to get on board and understand the basic statistics. And certainly in an hour, we can't get to any of that. But what I will try to do is point out some interesting twists that you really need to be aware of when applying the concepts of DOE. So there is a full day course offered through the SVC at the TechCon and on site. I am definitely willing to travel to deliver this course. And the full day course covers each of these topics in much greater detail. So the description, for instance, of design of experiments is not brief, but today it's going to be extremely brief. I'm going to discuss some key concepts in DOE, but I'd like to focus for a few moments later on underlying assumptions. And you need to keep those in mind as you go through practicing DOE. I will briefly mention a few DOE design types, not in anywhere near as much detail as the full day course, obviously. And then I will focus on complications that arise. And I had faced such complications and believe I found useful solutions. So that's what I'd like to share. And again, the detailed story is in the full day course. I will present a simulated plasma etch example, and then a real example from my work in plasma web treatment back in the Kodak days, and make some concluding remarks. So here we are with a brief description. In DOE, we talk about factors and responses. The factors are inputs or variables that determine responses, which are outputs or results or performance. So imagine you had a factor X, and there's this response Y that changes as a result of setting factor X. So at low settings of factor X, Y is increasing as X increases, and then it levels off, and then it eventually starts decreasing. That might be a response as one of your experimental or process factors. So now imagine you have many factors and a few different responses. This is a multivariate thing, but the basic premise is looking at responses as a function of factor settings. Now, when you measure that response, you don't always get the same answer. And a big piece of DOE practice that's important is understanding that there is response variation. That's a variability in results. It comes from a variety of causes. We'll discuss a little more about response variation as we go through the hour. But knowing that there's response variation and knowing what to do about it is part and parcel to good practice of DOE. Another interesting feature of DOE is all these factors are on a common scaled space. So you change the factors as much as you can in your experiment or your process, and you scale them to this -1 + 1 axis, and that puts every factor, whether it's temperature or speed or some other thing relating to shape or geometry, you can put all those factors on the same footing and make a quantitative comparison when I change this factor across its range in my process or experiment. Is it more or less important than another factor for determining a particular response? And finally, the design itself. What is this design we talk about in design of experiments? It's an experimental design. It's a set of factor settings. And those factor settings are points in a factor space. And they're points at which we measure these responses. So imagine a 3-factor space with orthogonal axes, factor 1, factor 2, factor 3. And on the left, I show a cubic factor space. And some of the corners of that cube are highlighted with coordinates here. But these are factor settings in the cubic factor space. Sometimes you might work in a spherical factor space, and the points will lie on the surface of a sphere. And those points also define factor settings. Now, some key concepts behind all of this are statistical leverage, for one. And when you look at statistical leverage, here's a quick example to explain that concept. Imagine you're measuring deposition rate as a function of power. If I take two power settings that are fairly close together and I have a response variation that could cause the measured deposition rate to go up and down as shown in these vertical bars, depending on my luck, I could come up with a negative slope or a positive slope or zero slope for deposition rate versus power. On the other hand, if I space those points far apart, then even with that same amount of response variation, I can unmistakably say there's a positive slope to deposition rate versus power, and I can know the slope fairly well. So that is the power of statistical leverage. And when you look at a design, this might be, for instance, a two-factor experimental design with 4 corners and a center point. Now, the fact that these corners are far apart relates to statistical leverage, okay? And the fact that there are very few of them relates to the idea that we're going to be fitting a fairly smooth and continuous function, and we don't need a whole lot of points to do that fit. On the other hand, you might be looking for some details on the benchtop that aren't a smooth and continuously varying thing necessarily, or might have wiggles and ripples, and you might need to sample in a very intense way. So here's that same two-factor space. And in a benchtop experiment, you might choose factor 2 at its average value and vary factor 1 in tight steps, and then choose factor 1 at its mid-range value and vary factor 2 in tight steps. That is called one factor at a time. It's extremely intensive, and when you're trying to do an economical experiment, and these experimental points, when you're running complicated processes and measuring complicated responses, can be quite expensive. So the parsimonious nature of DOE is played out in the design. You use only as many points as you think you need. It's like name that tune. You can name that tune in as few notes as possible. Another thing we do in DOE is we select the design to minimize factor correlations. There's this thing called the variance inflation factor, which I describe in detail in the one-day course, but here we'll just say it exists. It's a measurement of how much your noise becomes inflated by your poor choice of design. So a VIF of 1 is great. That's as good as it gets. If it's greater than 1, the way you've chosen your design points inflates the effect of noise. It makes it harder to be confident about your effects relative to one another, not only in confidence level of the effects themselves, but which effect is which. So on the left, I have a well designed set of points where if you were to look for effects of factor 1 and 2 and their interaction, you would be able to determine those things without the impact of variance inflation. This design, which also samples the same two factors on the right here, has an implicit correlation by the way those points were chosen, and it's at about a VIF of 5 for, I believe, 2 of the 3 coefficients in a model for main effects and interactions. And above 5, it's considered a significant correlation. So you're just setting yourself up for more difficulty, and you better have extremely low noise levels if you're going to get into a situation like the one on the right. And speaking of noise levels, we deal with response variation. We take countermeasures for this drift or jitter or natural variation or hidden factors. We take replicates. We must repeat a condition several times to understand what the level of response variation is, because that helps us set our confidence limits on our models that we create. We randomize the run order so that you aren't changing a factor in one direction over the course of the experiment, which might be confounded with drift. You randomize things, you go in opposite directions and switch things up. You might run sub-blocks of the design structure. So the 2 blocks run at different times, different parts of the experiment, might be able to give you a hint as to whether or not there's some drift or some hidden factor involved. And then we use the standard deviation from replication as the metric of what our response variation is. So those are some key concepts that are in the DNA of DOE, if you will. Some underlying assumptions that I'd like to highlight that are not expanded on as far as I can see in DOE courses. We should bear in mind that we are trying to create a model and generate a response surface. At the final stages of a DOE practice, you've whittled down all your factors to the most important, and now you want to create this response surface to help guide you as to where the good stuff is or what happens when you change these factors. And that surface is a mathematical expansion of an unknown function about a local average in a chosen factor space. So it's a mathematical model, and such a model might be for a response y, and that model is f of x1 through xn. You might have n factors. And it'll have linear terms, which are your main effects, x1, x2, x3, with their coefficients that will be fitted in the model. And these interactions, x1, x2, or x2, x3, or x3, x4, and so on. You can also have three-way interactions or four-way interactions. Typically, we only consider the two-way, but if you have good reason to believe there are other higher order interactions, by all means you throw them in. But at the end of the day, you've still got a polynomial. It's got linear terms, interactions, and quadratics. And again, while there might be quadratic terms for some of your n factors, you might have a quartic or a cubic term that you're concerned about. You would throw that in if you had information to suggest it. Typically, you're talking about a second order polynomial with interaction terms. So it's a fairly simple mathematical function that's going to describe this response surface. Okay, and we'll get back to what that means in a minute. The next thing is you're assuming that all the factors you have in your experiment are all the important factors. It makes good sense to ask yourself, are there other factors and issues to consider before you spend the bucks on the big experiment? So in cartoon, I've shown this little box. This is your process or your experiment. These blue knobs are your factors you can set. So we have 4 factors here. Something comes into the process. These factor settings dictate what's going to happen, and that's your response. And on top, I've got these gauges here, and there are things you can measure sometimes, and you know what they are, like it might be relative humidity, and you don't have a good way to control it except wait until fall to let it go down, or wait until summer to have it come up. But if you compare things in fall and summer, and you can, by design of experiment, show that the humidity matters, right? Now you might be thinking about, we might want to control humidity. So there are things you can measure, but you may not directly control very well, but you're aware of them. And so if you're careful in how you do your experiment, you can either nail them down so you don't confound anything, or you can add another knob here to tune those in before you go and do the experiment. At the end of the day, you've got known factors. They're maintained or controlled to minimize their variation. If you're going to study them, you're going to control them. If you don't care to study them, you at least have to maintain them well. And then there's all the stuff you missed, not considered, not identified. They're uncontrolled or hidden factors, and they're not your model. Another important assumption, the third big underlying assumption, is that any response you measure is going to be amenable to the standard DOE approach. It's going to be fit by a second order polynomial. And I think you'd agree that steps, spikes, and oscillatory functions are not amenable to such a mathematical fit. And we'll talk about what you do about that later. In addition, if your noise level's huge, your response variation isn't in check. Even if you had a smooth function, you couldn't tell what you did. And that's kind of like the statistical leverage example I gave earlier. But the point is, you can do all this fancy stuff and not have your response variation in check, and your model's meaningless. So let's talk briefly about common designs. There are 2 types I'll mention: screening designs and designs to model response surfaces. So first, the screening designs. Their purpose is to assess a large number of factors for their importance. And on the right here, I've shown a cube. This is a 3-factor space. Notice there are 4 points of the 8 corner points in that cube in this design. Why? Because in 3 factors, you have 3 main effects. So you have 3 main effects and an average value. You need 4 points to fit that model. There are your 4 points, a half fraction. And it turns out the other half fraction will give you the same information. All right. As n goes up, you've got min and max as your settings. Those are your 2 choices. You've got 2 levels. As the number of factors goes up, number of factors is n. You have 2 to the n possible corners of that hypercube. So a full factorial would grow as 2 to the n, but the number of main effects only grows as n. So it is much more economical to pick n of the 2 to the n points, or some fraction of those 2 to the n points, to run your main effects design. And that's the premise behind these fractional factorials. And you can find, in the literature, a fractional factorial for, any number of factors you care to study. And you'll find main effects which might be confounded with two-way interactions. And that's the warning. You might be confounding them. And in the literature, you'll find people sweep those two-way interactions under the rug when they're screening for factors. Sarah Cotter, on the other hand, came up with a screening design where she did not want to sweep those two-way interactions under the rug. And she has a design that uses 2 reference conditions, everything set high and everything set low, and then 2 sets of other conditions where you change from one thing set high to low or one thing set low to high, one at a time. So you have 2 reference conditions and 2n other conditions where you're changing one factor only out of that reference condition. For those 2n plus 2 design points, you run an analysis that then will find any factor that is important as a main effect or through interactions. Different philosophy from the half factorial or the fractional factorial. And then once you've screened your factors and you're going to go in for the response surface, you need to choose a design that has a number of points sufficient to determine the most significant effects for the n factors. And those effects could be main effects, interactive, quadratic, whatever. Any additional points in your design are important in that they provide degrees of freedom for assessing the quality of fit. But you don't want to go overboard with those additional points, which is the frugality of DOE. So here's an example of a central composite design, this cube. You have 8 blue points, those are the corners. If you run just those 8 points and the center point, you can fit a main effects plus interaction model using the center point to test that model. So you leave the center point out of the model, you see if it's predicted properly by that model, and if it is, a main effects and interaction model is for you. If you find a significant deviation of that prediction at the center point, you need quadratic terms. So what do? You add these face centers, these 6 points, and those will help you fit a model that will have quadratic terms in it. So this is a nice way to do it because you do it in stages. You do as much as you need to ascertain whether or not you need a more complicated model. Then you go in and add the points as needed for that more complicated model. So in that -1 + 1 factor space, you have your settings dictated by the design you choose to use. Then you have to translate those to your experimental or your process space. So you invert the process from converting experimental stuff to the +1 - 1 axis. You take the point in that +1 - 1 axis, multiply by the span, the max minus min setting in your experimental space, divided by 2, and add the average of the max and the min. And that's how you get the condition you're going to set your experiment to for that design point. And when you do that, you get your responses measured, you go back to the +1 - 1 space, and you fit that response to this model, in this case, a 3-factor full quadratic model. Notice there's an average value. There are 3 main effects in the +1 - 1 space. There's A times x1, A2 times x2, A3 times x3. There are 3 pairwise interactions, and then there are 3 quadratic terms. So 10 coefficients in all, and you'll notice that this design has more than 10 points when you add the red guys. And so you do have extra degrees of freedom to assess the fit, but it's not like we're going to do 20 points or 40 points. So that's all fine and good. What are some complications that arise? First of all, let's start with choosing our factors. That's an important thing. You can find factors, and I have found such factors, that act together to produce a result, and you know how they act together based on physics or science. And if you know that, why leave it up to the model to figure it out? You're going to waste precious coefficients on something you already know, right? So you want to put that in at the outset. And that's the least of it, is having the extra coefficients. The worst of it, the most of it, is you could get a very difficult situation fitting the thing because it's such a strange relationship. It doesn't map well onto a simple polynomial. So if you know that stuff going in, clean it up before you choose your factors. So here's some examples. Imagine your process produces an exposure of a surface, right? So here's a surface, I'm exposing it to a flux density of something. It could be light, and I'm doing like exposure photographic film. It could be ions, and I'm bombarding a surface. It could be gamma rays. It could be sputtered atoms that are coating a surface, right? And what we know is the denser this cloud of stuff, the shorter time it takes for this surface to get filled up, right? So we already know that this meaning of time is directly related to the density of this flux. Okay, so flux density times time would give you dose. That dose is your factor, not time. Dose is your factor. Now, where would flux density be important? If the cloud got denser and things happened in that cloud and they started interacting with one another, you might see a dependence on flux density on how things turn out. So yes, keep flux density as a factor, but time is only going to be used to adjust the dose. So time is not a factor. It is a servant to generating the dose, okay? So we would have flux density and dose as our factors, and time would be adjusted to provide the factor dose to the right setting. Another kind of example, you might run a process with an input voltage. There might be a resistor in there that adjusts the current going through the process. And that resistance isn't so important, but you are twiddling that resistor value. But V squared over R, which is the power going through the rest of the circuit, as well as that resistor, that V squared over R, V times I here, is going to be more important to the process perhaps. The voltage level might be important. Things might happen differently at higher voltages than low, but your factors are going to be power and voltage, not resistance, okay? Now in the Webb treatment area, you apply power to a treater, power per unit width of electrode. The length of the electrode determines the exposure time of this Webb moving by. And you end up with this thing where power per unit width over line speed is going to give you the energy dose to that Webb. And that is an important factor, as well as the power in the treater. But the Webb speed is not an important factor except in setting that dose. So I hope I've given you a few examples of where setting up your factors to ask the right question is important. Now let's look at those responses. As I said, we're assuming those responses are friendly. And I think you'd agree that the step function response or the spike or this oscillation is not friendly in the classic DOE sense. So imagine there's a factor that produces the step response or this spike response or this oscillation. You can ask a question like, does the position or height of the step depend on other factors? Does the position or height of the spike depend on other factors? Does the amplitude, period, or phase of the oscillations depend on other factors? And when we ask those questions, we've already said that the factor that produces that nonlinear response is not going to be treated as a factor. It's going to be a second dimension in the response. You now have a two-dimensional response. It's this plot of this initial response versus that factor. So that factor is now folded into a two-dimensional response. And we will come back to that point. I will now point out another type of nonlinear response, which is saturation. And that's the one I have had to face head on. But in a simple example here, imagine your surface is taking something up and eventually it becomes saturated. And it happens with time. When the surface is uncovered, the uptake is linear with time, and as the surface becomes saturated, it flattens off. So there are two regimes, the short time regime where there's a linear slope, and the long time regime where it's just flat. And those two regimes provide different information about the process that is driving the response. So I've heightened your awareness to some underlying assumptions and some issues with response, the nature of the responses you're trying to measure. And so now I'm going to go into some simulations of what could happen. I'm going to start with a simulated main effects and interactions example. And this is inspired by Coburn and Winter's article on argon ion and xenon difluoride etching of silicon. This is relevant to the semiconductor industry. And they discovered that these ion and neutral fluxes, when acting together, produced a synergetic effect. So we will generalize this, and I'll use factor X1 as reactive neutrals and X2 as ions, and the response is going to be etch rate. And there are only two factors, so we can do a very economical two-factor central composite with a center point. So that design would have 3 center points because I'm replicating the center point 3 times, and then the corners of that square coded in 1 plus, plus or minus 1. And notice that the 3 center points don't repeat identically. And that's because when I constructed this simulation, I chose values for these terms, the main effect of ions, main effect of neutrals, main effect of the interactive effect of ions and neutrals, and the average value. And then I took each experimental calculated etch rate and threw in some noise. The amount of noise was, it was selected from a normal distribution with a sigma of 5% of the value. And I set my spreadsheet up to do that, so every time I hit go, these points all are buffeted around by this 5% noise chosen from a normal distribution with a sigma of 5%. And so anytime you run this, you'll get different answers as much as dictated by this noise. So here's my pseudo experiment with these 3 center points, and they show up here, and then all these corner points. And what I'm plotting here is the etch rate against the neutral flux with different settings for the ion flux. In blue, the ion flux is set low. In orange, the ion flux is set high. And you see the slope of that response to neutral flux is heavily dependent on the ion flux. That is a typical synergy effect. We also notice that the center point is well centered between these two lines, which says that the main effects plus interactions model is adequate. And when you actually fit to those coefficients and generate the response surface, this is what that response looks like. That's your standard twisted plane response, that each factor enhances the effect of the other. In this case, there are other cases where that plane twists differently, and the factor, the factors can actually change the slope to negative instead of making it more positive. Now, that's a nice example from the benchtop. Imagine taking the benchtop stuff and throwing it into a real tool that etches silicon wafers. You don't have a knob that adjusts the neutral reactive beasts and the ion beasties. So you turn knobs that look like power or pressure. Instead, you flow some gas into an etch tool, you crank up the power, and you etch away. So your process factors are power and pressure. And both of those factors interact to create ions and reactive neutrals. And what typically happens is as power or pressure increases, at some point you get a deviation from linear behavior because of loss effects. At the high powers and high pressures, there are losses that come in that rob you of some of the stuff you were trying to create in excess. And so you get a leveling off, if you will. So that loss in linearity means that your model is probably going to need some quadratic terms. So now I've revisited this example. I have added, and they're grayed out here, but I've added 2 quadratic terms, a power squared and a pressure squared. I've added them to the calculation. I've thrown the same 5% sigma noise on everything. But I've grayed these out because we're going to try to fit this to a main effects and interactions first. And we look at this plot, this main effects plot, to see if that's even possible. And what you see is, yes, we have a synergetic effect as we did before. But now look at where the center point lies. The three replicates suggest that we are a good bit off center. Halfway between this blue and yellow line would be right around there, and we're north of it. So there's a warning. We probably need quadratic effects. So now I'll throw those in, right? First, I have to take those extra points. So I take the orange point to the right, the orange point to the left, the blue point south, and the yellow point north. So those are my four face centers, if you will, or they're the edges of that square in process space. And you can see, if you squint, that there's some evidence of deviation from linearity when you actually fit these simulated noisy data with the 5% noise. You simulate them and you go ahead and take the simulated data and model to this full expression with the full quadratic model. You end up with this response surface, which is not a twisted plane. It's a twisted plane with a little dome added to it. And you can see that the model can mimic the curvature in the data set and predict the center point properly. So now I've given you a concocted experiment that I simulated to illustrate some points here. Now I'm going to show an example from my work at Kodak in plasma web treatment. And we'll actually see, some of the issues I had to wrestle with while doing this work. I'll just give a background in polymer web treatment. Polymer webs, they're big rolls of thin plastic sheet or thin polymer sheet. And they're used in manufacturing processes for so many things. To name a few: candy wrapper, aluminized mylar balloons, and photographic film, which of course was interesting to Kodak at one time. So the polymer has desirable properties, typically mechanical properties, cost, other things. And the price you pay for gaining those benefits is that surface is generally not reactive with the coating or the finishing process you're going to do to create your product. So over the decades, people have found that exposing these polymer surfaces to plasmas, such as glow discharges, dielectric barrier discharges, even flames, which are a type of plasma, those things can modify the polymer surface chemistry. And in general, there are nitrogen and oxygen-bearing plasmas that have been proven to provide adhesion promotion solutions in the web coating industry. And I'm going to talk about an example of a nitrogen-bearing plasma. So how does the plasma web treatment process work? Imagine a big vacuum chamber where you have a roll-to-roll conveyance system. You have a web drive, an unwind. It transfers that web through a treatment device to a take-up spindle, and you wind the stuff up when you're done. You can apply power to this treatment device. You can flow working gas through the treatment device. And the web speed and the source length in the web direction control the residence time, the exposure time, if you will. The power and the source width control the power density. And you end up with dose as power per width over web speed. And that dose, as I said, might be a possibly important thing. So initially, you might look at this and say power, pressure, web speed are your factors. You've heard all my warnings about speed and time, because speed here is controlling the exposure time. I hope you've heard my warnings about treating that as an equal factor. So we might consider something like dose. And there's yet more to be said about dose as we go on. But for now, let's dive a little deeper into the plasma source. This is a coplanar electrode system. It's capacitively coupled, driven at 40 kilohertz. We create a nitrogen plasma above that, and this polyethylene naphthalate, polyethylene 2,6-naphthalate web, which is a photographic support, is transported through the plasma. And that web takes up nitrogen as part of the process of being exposed to the plasma. And what you see here is nitrogen incorporation versus dose. X-ray photoelectron spectroscopy is how the nitrogen uptake is measured. In addition, we get chemical information about that nitrogen, but we do not have time to go into all the details about why some nitrogen isn't the same as other nitrogen in that polymer surface. But treat it now as a practical response that is a good predictor of the adhesion and durability that was the end goal for this treatment. So now we have process vectors, power, pressure, web speed, or possibly power, pressure, dose again. Let's add another layer of complexity. We're going to add an ion flux probe and an optical emission spectrometer. The ion flux probe can tell us the ion flux hitting the web. The optical emission spectrometer can be used to sense N atoms, dissociated nitrogen, highly reactive, I should say. So the N atom concentration will relate to the flux of N atoms hitting that web. So now we have measure of ions and neutrals. And this should sound familiar based on that first simulated experiment that I discussed. So now we have some mechanistic factors, ion flux, neutral flux, and this web speed, which we now understand is not a good one, right? So we'll fold that one into dose. And we could imagine that the effects of ion flux and neutral flux might be impacted by how we obtain the dose. But there's more to the story. Let's look at the nitrogen uptake versus dose. We have a saturation response. This is nonlinear. We should not be putting dose in as a factor. Dose is part of our response. We will change the factor dose to generate the nitrogen incorporation, and we will use web speed to maintain the dose at the setting we care to have. In this experiment, we chose a dose range of 0 to 4 joules per centimeter squared. And notice these sets of data, the circles are all at the same pressure, the squares are at the same pressure, right? So you change the shapes, you change the pressure. And notice that when the shapes change, there's a noticeable difference in the dose response. So that pressure is changing the dose response in some fairly subtle way. And the power, if you compare the dark and light symbols, the power is also changing the dose response in a more subtle way. So you can see just from the end game, the way this design of experiment was set up, using dose as part of the response, I can now look at issues like how does pressure or how does power affect the dose response. Now I do not have time to go into all that gory detail of what the experiment was and how it ran and all of that. So I'll give you a synopsis. The two responses I chose to look at are the uptake rate at short times and the saturation value at long times. And again, that's the slope of the dose response at low dose and the saturation value. And when I analyze those two factors in the process space using power and pressure, I cannot do a good fit with a main effects and interaction model. And the results would tell me I need quadratics. And as you'll notice above, the data above here, I didn't take any more points. I've just got those 5 points. So, and notice I said points, 5 sets of dose responses, right? So what can I do with the 5 points I got? If I look in the diagnostic space and look at what the ion flux and N atom density was at all those conditions, I actually get a very good fit to main effects and interactions model for the uptake rate at t equals 0. And I can look at the saturation value, but it's fairly complex, and I'll show you a little bit about that. Again, if you want the gory detail, I recommend the full day course. But this model that I'm going to fit to, it uses only main effects and interactions, but it's not your standard main effects and interactions model. So to understand how we get that saturation value modeled properly, I'm going to take a little trip into the realm of surface sites, the surface sites model. So imagine you have a polymer surface and the molecular structure dictates what parts of that polymer surface are receptive to this active nitrogen that's going to incorporate. You only have so many sites per square centimeter on the polymer surface, and that's N max. And at those sites, you can get the chemistry you want, and this flux density gamma of particles will produce occupation of these sites. And I will now call those particles incorporating particles. Those blue ones that incorporate have a flux density of gamma sub I. I don't know who they are yet, but we know they incorporate and form nitrogen. Those same particles can actually cause loss of nitrogen. So we'll call that flux density gamma sub L, okay? And gamma sub L, or the red guys, they can come into an occupied site and knock the blue guys loose, all right? And it just so happens the red and blue guys can have exactly the same identity. An ion can incorporate, an ion can sputter something loose. A neutral atom can incorporate, reactive neutral can abstract it by chemical reaction. But for now, we're going to just call them loss and creation, or loss and incorporation particles. So what you find is if you solve the differential equation, first set it up, the rate of change of that nitrogen on the surface as a function of time is going to be proportional to the incorporating flux times the unoccupied sites. And there'll be a loss term. So you'll have to subtract off the loss flux times the number of occupied sites. And when you solve this, you get the answer shown in the middle, which simplifies to n final times 1 minus e to the minus t over tau. So it's like a charging capacitor. Now let's unpack this middle equation. So if you just look at the differential equation from the outset, in the limit of no nitrogen in the surface, the only thing that's important is this first term. And you can find out that the NDT at short times is just proportional to the incorporating flux density times N max and a reaction coefficient. In the saturation regime, where this exponential vanishes at long time, you're stuck with this term here. Notice that that's the incorporation flux over the incorporation flux plus the loss flux, all times their respective coefficients. Now I can ask what is in this gamma sub capital I and what is in this gamma sub capital L. What can incorporate? Well, molecular ions or atomic ions can hit the surface. The ion flux probe doesn't know which one it is, so we'll just call it ion. So those ions can hit the surface and interact and form a nitrogen bond. But a neutral N atom can do the same thing. It's very reactive. And maybe there's some synergetic effect. So that's why we have the interaction term there. And in similarity to the the silicon etch example, those ions can etch things free. Those neutrals can abstract things. And then there could be a synergetic effect, as was seen by Coburn and Winters. So I have two different main effects and interaction models. And I can fit the first one by standard DOE. I just fit this thing to the uptake rate that we measured. But this response is not a simple main effects plus interactions. It's the quotient of a main effects plus interactions over a sum of main effects plus interactions in another one. So once I've solved for this main effects plus interactions, I can put it into this model, and now I can solve for this. But this is my model. It is not a simple main effects and interactions. It's some previously determined main effects and interaction model with this other guy that we're trying to find stuck in the denominator. That does not look like a simple response surface. And to prove my point, here's the uptake rate, a very simple twisted plane in the diagnostic space. And here's that crazy main effects and interactions over two main effects and interactions. And you'll see that it's a very flat response that deviates only when ions and neutrals are at their low settings. More so in the corner here. So again, not much time to go into detail, but I think it's an interesting example. And it's interesting to ask ourselves, what do we get out of doing an experiment in the process factor space versus doing it in the diagnostic space? Well, we're controlling the process factors in the design. So yes, process factor space does control the process factors in design. And yes, that's what we did in the plasma diagnostic space, because we piggybacked the diagnostics with this process space experiment. We can ask, are the causal factors controlled in the design? Well, in the process factor space, not necessarily. And in the diagnostic space, we hope we're measuring some causal factors, but we're not controlling them. We're letting them vary as we change the process settings. And then we're recording what we saw. The measurements we're doing in the practical response realm with the process factor space is we're just measuring the practical responses. So we would just measure nitrogen uptake, adhesion, whatever, at those settings in the process factor space. But when we piggyback with the diagnostics, we are adding a set of measurements that are aimed at getting at factors rather than responses. We're putting those diagnostics in addition to those practical responses. And then when we generate response surface models, in the process models that you get in the process factor space, yes, you have a response surface model for that process. When you add the plasma diagnostics, you end up with potentially a plasma modification model, which you saw me sort of unpack at the end. If you want a process production map, or a production process map, I should say, you obtain that directly if you work in the process factor space. If you add the diagnostics, you might be thinking about new process factors to consider. If you're looking at technological improvement, the process-based stuff is what you get out of a process factor space design. You'll get a process improvement. If you look at the plasma diagnostic space, you might get a mechanism-based improvement. So with that, I'll make some brief conclusions. Design of experiments is well developed, routinely applied. It's quite useful. And you know, there are a number of reasons to use the designs. And I'm going to sort of curtail my conclusions and move ahead. I think most of you are aware of the benefits. But I'm going to look at some things to be aware of. Some key concepts of DOE actually work against each other. So your design points span as wide a range as practical to get statistical leverage. And yet, mathematically speaking, the fit to the model is an approximation that works best in the limit of small changes. So what should we do? Make big changes or small changes? The answer, of course, is you strike a proper balance between gaining statistical leverage and making good approximations. And the response variation is the determinant of how you strike that balance. Another thing is looking at the responses themselves. You've got to avoid improper use of DOE models for things like saturation responses, spikes, steps, oscillations, and so on. Not all factors and responses are best used as is. Some factors are implicitly interactive or reciprocal. I've presented you with some scenarios where that happens and suggested we combine factors as appropriate, for example, to create this dose factor. And you still will vary some independently, while others you'll vary the combined effect, treating one of those other factors as kind of a surrogate. Now looking at the response side of things, some responses are inherently nonlinear. And so you really need to combine a factor and a response to map out the nonlinear behavior, and you now have a two-dimensional response. It's more work, but doing a little more work and getting a lot more information is better than doing less work and getting nothing. And I do maintain that if you don't pay attention to this kind of stuff in the face of nonlinear responses, you will get mostly nothing. So in addition, once you have a nonlinear response identified, you'll find that those responses have different regimes often, such as spikes and steps. And so you use behavior in those different regimes as separate responses. That is a valuable thing, and I've demonstrated that using the initial slope and the saturation value of the uptake curves. And then let's just admit that some responses are just plain complicated. So we can apply these concepts to advantage at different stages as we peel the layers of this proverbial onion, or metaphorical onion, I should say. We screen factors, we map processes and do optimization. We then start relating factors to physical chemical quantities that we measure, and then we can further relate those quantities to responses and develop physical and chemical models. And this is my cartoon of that metaphorical onion. And if you look through the layers of the onion, we start with a simple process understanding. We add detail as we go down to each layer. The second layer, we start understanding there's a thing such as dose. It's important to measure the delivered power, not the power on the power supply front panel. What is your gas flow at the pressure you're using, so on. You go down to the next level where you start putting in some diagnostics to worry about ions and radicals. And then you can take it, deeper and deeper. And this fourth layer of the onion is not the last layer by any stretch. Every step of the way, you're getting new understanding and applying it. So with that, I will open it up for questions, and also mention and advertise that there are more webinars in this series coming down the pike. I thank you for your attention, and I will be happy now to answer any questions you have.
So, Jeremy, thank you very much. On behalf of everyone, that was an outstanding presentation. To our attendees, I have turned on or unmuted all of your microphones, so you have an opportunity, or we have an opportunity for a bit of group discussion. There are two questions, one that Maya has submitted and one that Ben has submitted. So Maya, let's start with yours first. You can address that to Jeremy. Ben, you can follow, and anyone else that has a question, please be patient. We've got all the time in the world here.
Hi, first, thank you for such a great presentation. My question is, what kind of simulation programs do you use when you explained all the models, and what do you recommend?
Okay, so let's make a distinction between simulation and fitting and doing the statistics. So to do the simulations, I did this all on a spreadsheet, and I used all the power of the Microsoft Excel statistical tools to throw the noise into the model I was using to generate the false experimental data that I would then reanalyze. To do the actual analysis, back when I was at Kodak, I used this thing called JUMP by SAS Institute. And in my full day course, I do mention a number of software packages. I believe that Minitab is now a very common one in industry. There are all kinds of tools. So you can find everything packaged in Minitab, for instance, or JUMP. And there's another kind of tools that allows you to use your Excel, and it uses all the routines in Excel, but it creates an interface to that, so you don't have to design your own spreadsheet tool. So there are a number of ways to get at the stats, but basically you're doing linear regression to a multivariate model. And that's a very common thing that can be handled now in Excel, and all these tools, JUMP and Minitab, do that work as well. The advantage of having the software package is they typically come with a library of designs, and they do the statistical analysis in the DOE lingo, whereas in Excel, you're doing all that statistics, but you have to kind of know what you're doing. So you have to know what those tools do in Excel and what it is you're calculating. But it's really nothing more than a least squares fit to a bunch of coefficients in a polynomial model. And the number of points, the number of equations you're generating is the number of experimental points you have, and the unknowns are the coefficients. Does that answer your question?
Yeah, thank you. If I may, I have one more question. When you said that it gets complicated with some responses, when do you say this cannot be done? When do you say this cannot be fitted or explained?
Yeah. So think about the mathematical nature of the relationship you think is between the two factors. So time and flux density, they work in product, right, to produce this dose. So you would have to have in your model something that implicitly has the product of time and flux density, all right, to get the physics of it. If you waste a separate factor on those two things and hope the model is going to come up with that relationship, particularly with the frugal sampling of the space, you're stressing the system too much, I believe. And then to your question, if you find a reciprocal relationship, and I think when you go through the math, you'll find out that some of these relationships would force your model to come up with a 1 over something. And a polynomial isn't the best way to fit a 1 over x, okay? And so you're going to start running into problems there. And then the next level is when you look at the responses, and if they're inherently nonlinear, then you really have a mess. So on the factor side, by folding the effect of factors in together and treating the combined effect as a factor, you can find out if that combined effect has a linear or interactive effect. Excuse me. And on the response side, you can find out if there is a factor that drives nonlinearity and take it out of the factor set so that you're not forcing the model to find that nonlinearity. And you put it in the response side of things. Does that make sense?
Yeah, thank you.
Thanks, Maya, for the question. Ben, you have a question? Do you want to unmute your microphone, or should I read it for you?
Hi, Jeremy. Thanks for the presentation. So if one is just taken like a basic introductory course in probability statistics as an undergrad in their science or engineering program, what kind of books would you recommend as sort of like the Bibles of DOE for a beginner?
Yeah. So honestly, I learned it because my group leader hired Dave Doller to come to our group and teach it. And we had a 5-day intensive course. And so he discussed the relevant statistics. But what I have found is that the statistical capability of things like Excel allows you to go in. You have to do a bit of legwork on the web, but you can find out, you know, what is a VIF, and you can teach yourself how to calculate it. There are some basic books of DOE. I would recommend you pick one that's relatively old and one that's relatively new. Off the top of my head, I don't have any titles for you, but I would just look up that topic and pick something from the 80s, you know, and then if there's something more recent, I would pick that to see what's new. I will say the manual for JUMP, and more than likely the manual for Minitab, has a lot of this discussion in it. But some of the things you will want to know about are things like if you're going to create your own model, or if you are forced to deviate from a design you were trying to use because you can't set the process factor settings all where they need to be because you're reaching some limits, you will want to know if the design space you ended up with has bad VIFs, right? So you'll want to know how to calculate that for yourself, I think. And I mentioned that in my course and mentioned how it's done. It's not that complicated. I taught myself by poking around on the web. There are some YouTube demonstrations of how to do that, by the way. In terms of analysis of variance, that's a very common thing, which might not be covered in detail in a DOE book, but it's something you need to know because the DOE principles are based on analysis of variance. So you have to know what these t-tests and f-probabilities are and all these things that help you understand how important is that coefficient I just found. And again, these canned software packages often have guides to that, or they will do that understanding for you, and you're kind of at their mercy at picking the winners and losers. The Cotter design, the only place I've seen that discussed is in Cotter's article, and a colleague of mine at Kodak drew attention to that article for our group, and I got a copy of that article, and I've used that Cotter design for screening several times, and I think it's a wonderful way to do things, and I discussed that in detail in the one-day course. But that one you'd have to look up Sarah Cotter's paper, and she explains how it's all done, how you do the analysis, and so on. And so does my full-day course. But I haven't seen that discussed. I have seen articles throwing darts at it. But I think the darts are misguided. I think it's You know, it bothers a lot of statisticians because it looks like a one factor at a time experiment. And that's a visceral reaction they have because it's fairly intensive for a screening, but it gives a lot of information. I hope that's some help. I know I didn't give you some titles to go for.
Right, thank you.
You've got a wonderful motivation to take the full day course. Pardon for the commercial approach.
Yeah, by all means.
Does anyone else have any additional questions? Well, with that, Jeremy, let me thank you again for putting on a absolutely spectacular 1 hour overview of a most complicated but yet most important subject for us. So again, thank you very much.
My pleasure.
And folks, just remember, this will be up on the SVC's YouTube channel within 24 hours.